This conference will now be recorded.
Everyone, the first topic is Van der Waals equation at high pressure and low pressure, because Van der Waals equation we have already seen it in the last class, and then there will be some problems related to it. Then we'll start liquefaction of gases, and from liquid, that is how gases can be converted to liquid, that is actually liquefaction, and also critical constant and importance of critical temperature, and after that liquid state, because until now we are discussing all about gaseous state, but in this chapter there is also liquid state topic that is also there. So Van der Waals equation, we know what it is, that we have seen in the last class. Now we have to see that if we change the pressure at high value, then what will be the effect on this equation. So when the pressure is high and when the pressure is low, two different conditions, and based on this we have this question also. So when we will solve this question, basically you will also be able to understand how this pressure is affecting the equation. So if we simply consider the equation, it is P A by V square and V minus small b. So I'm writing this equation only for 1 mole, so I'm not writing the small n value. Okay, so normal ideal gas equation that we know, that is simply PV equal to nRT. If it is 1 mole, then it is PV equal to RT. Now when it is converted to Van der Waals equation, which is basically applicable for real gases, not ideal gases, PV equal to nRT, that is applicable only for ideal gases, but if you want to deal with real gases, you have to consider Van der Waals. So now this equation is changed to P plus A by V square. This is the new term which is added to the pressure, and B, small b, that is subtracted from volume, and right hand side there is no change, RT for 1 mole. If it is n moles, it will be nRT. So this equation in red color that I have just written, which is Van der Waals equation. When pressure high, what happens? Now when pressure is high, this term P plus A by V square, just focus on this. So now P is very high value. So compared to P, you can ignore this term. That is, you can ignore A by V square term. So if you do not write this term in the Van der Waals equation, this equation now change to P plus, as if there is nothing, P plus 0, V minus B RT. Or I can write PV minus PB equal to RT, or PV equal to RT plus PB. So now you can see, look at the options, it is matching with which one? It is matching with option C, right? PV equal to RT plus PB. So when pressure is high, basically we have to ignore this A by V square term, because P is very high. So compared to it, this term, if we neglect it, it is okay. So this is the condition when it is high pressure. Under that condition, how the equation will be, that we have seen here. Next, we have to see if pressure is low, then the Van der Waals equation, basically here also we will solve another problem, but when you will solve this problem, then also you will be able to understand how this equation is changing at high pressure and low pressure. So here it is low pressure, and it is already mentioned in the question that Van der Waals equation is written like this: P plus A by V square. That means this term is still present, but in V, normally what we do in Van der Waals, we subtract small b, but here simply capital V is written, that is simply the volume is mentioned, and right hand side as usual RT, and this is for 1 mole. So this equation is already given, which is applicable at lower temperature. So it means what, that is summary, what we can say, when it is low pressure, you can ignore this term small b, because small b means what? Small b means the volume occupied by the number of particles of gaseous solid. So suppose we have this container, here we have different particles of gases, but suppose you just concentrate all the particles together like this. So see, compared to the total volume. Now this total space available in the container, the volume of the molecules, just if you accumulate it, you will be able to understand how small it is compared to the total space available in the container. Now when it is high pressure, what happens? Now the volume, suppose it is initial state. Now suppose the volume is decreased. Now with respect to this total volume, the volume of the gas particles are, you cannot say it is negligible. So that is the reason when pressure is high, this volume is not negligible compared to the total space available. But when pressure is low, now you can say that the volume taken by the particles, gas particles, all the gas particles present, that is negligible. So that is the reason now you can neglect this small b. So at low pressure, you can neglect small b. When it is high pressure, you can neglect a by b square because the term p is very, very high compared to a by b square. So b, if we neglect, the equation will reduce to like this. But in this question, it is asking that we have to find compressibility factor, Z. Fine. So first we will write this equation as it is given in the question. So see here, B term is not present. Then P into V, that means PV. And if we multiply A by V square with V, it will be A by V. Now keeping PV term in the left hand side, if you bring A by V right hand side, you will get this equation. And next what you will do, in the next step, both sides of this equation, you have to divide each term by RT. So PV by RT you are getting in the left hand side, and in the right hand side RT by RT, so it is 1. And A by V, if we divide it by RT, it will be A by RTV. Now Z is nothing but PV by RT, this ratio, right? So Z value what we are getting from this equation, 1 minus A by RTV. So this option is met, right? So in this way, solving these two problems, now we are able to understand how Van der Waals equation will change from the original format, which is P plus A by B square into V minus B equal to RT. So right hand side RT term, there is no change, but when it is high pressure, you have to ignore this A by B square term with respect to very, very large value of P, and if it is low pressure, then you have to neglect this small b compared to this volume V. Fine. Another equation which is based on this modified Van der Waals equation. So you can understand this equation not exactly like Van der Waals. It is saying that it is P equal to RT by V minus B. Or you can say this equation is basically like this, P into V minus V. If you bring V minus V towards left hand side, so basically this equation is just like the equation that we have seen in the previous slide. When you are getting this, when pressure is high, then only A by V square term negligible and the equation is reduced to like this. Now read the question. It is saying that at a given temperature T, that means capital T, temperature is fixed, and you have these 4 gases, neon, argon, xenon, krypton, all are noble gases given. It is found that all of them are deviating from ideal gas behavior, and the equation that they are obeying is given here, already given. Now what actual question? Here small b is the Van der Waals constant that we already know, and which gas will exhibit steepest increase in the plot of Z versus P, that means compression factor versus P. So basically you have to draw the plot Z versus P. That means you have to draw the plot where PV by RT will be in the y-axis, that is actually Z, and B will be in the, pressure will be in the x-axis, that is Z versus P curve. So this equation, we will arrange it in such a way so that you can get the term Z. So to get the term Z, basically, you have to find this PV by RT term somehow. Then only in that ratio you can write Z. So PV V minus V RT, this equation, how we are changing it? See, first multiply P with V and P. Then we are getting PV minus PV equal to RT. Now both sides of this equation divide it by RT. So in the left hand side you are getting PV by RT and minus PB by RT. Right hand side it is 1. So bring this term in the right hand side. So ultimately you are getting this. So our purpose is to arrange the equation in such a way so that you can get this term. Which term? You have to get this term because ultimately you need that equation from where you can draw the plot of Z versus P. That means Z versus P means Z will be in y-axis, P will be in x-axis. So if you want to draw this curve, obviously you have to find the corresponding equation. Otherwise, how you will draw the plot? So that is why the equation that is given in the question, we are arranging it in such a way so that you can get the term Z, which is nothing but the ratio PV by RT. Once you have obtained it, you have to compare this equation with y equal to C plus mx because two terms are there. So it cannot be y equal to mx. It is C plus mx. So intercept is present. So y is Z. This is intercept 1 and x is basically b. That means rest of the part. Sorry. X is not b. X is basically p. This is x. That means b by RT is slope. So m is slope, which is basically p by RT. B by RT, not p. Now it is asking in the question, which gas will exhibit steepest increase? Steepest increase means what? Slope is high. When slope is high, then only you can get some steepest increase. So just for example, suppose I am drawing two graphs. In one graph, there is intercept obviously. It is like this. This is the intercept and this is slope. How you will understand the slope? Okay, let me draw the next one. So this is suppose type 1. Another one I am drawing like this. So you can understand here it is very, very steeper compared to the previous one. And how to understand slope? Just take any 2 point. If you make this type of triangle, here also just take 2 points and join it, you are getting a triangle, right? Now in this triangle, this distance is basically y distance. That is, if you take the corresponding distance in y-axis, and this distance is the distance in the x-axis. So this y, better I write here b by a. So this b by a is actually the slope, which is very, very high. So higher is the value of slope, higher, more steeper will be the plot. Similarly, if you take the same ratio here, you will see here a is very, very large compared to b. So that is why slope is less. So I am trying to say that when it is mentioned that steepest increase, that means slope should be very high. When slope is high, when b is very high, because R is constant, temperature is constant. It is mentioned in the question, given temperature, that means temperature constant. So in the slope, the variable part is only small b. Okay. So when b is max, then you can say slope is max. B max, m is max. That means it will be steepest. Fine. So now look at this graph. We have taken z in y-axis. We have taken p in x-axis. This is intercept 1. And if you take any two lines, basically you will get the slope. But slope is basically b by RT on where only b is variable. So when b is very, very high, it will be very steep. That is the nature of the plot will be very steep. Now b high, how you will understand? Because Ultimately, from these four options, xenon, krypton, neon, argon, you have to find which gas will exhibit steepest increase. That means it is basically asking which gas will have max small b value. But it is not directly asking. It is asking in terms of steepest increase of the plot. But actual question is in which case b value is max. Now remember, B is basically related to volume, and volume high when atomic size is very high. Now if we look at these four options, in which case atomic size maximum, that means highest atomic number, all are noble gases. So highest atomic number is for xenon, right? So here when B is increasing, basically slope is also increasing because M is increasing. B by RT is M. Now B is volume occupied by the particles of the gas, and xenon among these four gases is having the maximum atomic size. So it will have highest volume, because if you want to know volume formula for sphere is, if you consider the atmosphere, it is 4 by 3 pi r cube. So when R is high, obviously volume is high. So correct answer will be xenon. First option. So this problem is related to A and B value. That is small a value, small b value. Here four gases are given, and for the four gases, the small a value and small b value, Van der Waals constant, these two values are given. Fine. A, B, Van der Waals constant already mentioned. You have to find the correct statement about the gases. Now, if you look at the information given for A and C, A is, that is small b is same. A and C, B is same. Similarly, if you consider the other two gases, B and D, here the value of small a same. So for B and D, A is same, but B different. And for A and C, B same, but A different. From this information, you have to find the correct option. So basically, if you look at these options, gas C will occupy more volume than gas A. This is also same. So 1 and 3, first part same, but 2 and 4, first part is opposite, lesser, lesser. Similarly, if you look at the second part, option 1, B is more compressible than D. This is also, this is more compressible than D. And these two, last part, option 2 and 3, the second part is saying that lesser compressible than gas D. Now, from this small, that is critical constant value, A and B, how we can reach the conclusion that in which case volume will be high, in which case compressibility will be easier. So you have to follow this logic basically. So if value of B for two gases are same, but values of A different, that means if you consider A and C, here B is same, B same, A different. So when you have this type of situation, then the gas which is having larger value of A, because here A is variable, so the gas which is having larger value of A, that will have lesser volume. Now among A and C, C is having larger value of A. So among A and C, A is having value of A 642, C is having value 431. That means A value, it is A greater than C. Fine. So when this is the case, which is having larger value of A, that will occupy lesser volume. That means A will have lesser volume. So C will have more volume. Now C is having more volume that you are getting in option 1 and 3. So we can cancel these two. Now why it is so? Since it will have larger force of attraction. We know that B is same, fine, A is different. Now A is directly related to intermolecular interaction. Remember when we have discussed van der Waals gas, what is the significance of small a, what is the significance of small b, that I have already said. Fine. So A value high means what? Large force of attraction. So when there is large force of attraction, basically lesser distance will be present between its molecules. Now if lesser distance is present, obviously it will take less volume. So when A value order is like this, then volume order will be opposite. Now C is having more volume than A. So according to that logic, any of these two options, that is 1 or 3, will be correct. Now for B and D, A is same, B different. Now if value of A for two gases are same but values of B are different, so B different for capital B and D. So in which case B is high? See 0.4382, 0.041. So if we compare B value order, in that case D is having more B value compared to capital B, because it is 4382, small capital B is 04136. In this case the value of B different, then the smaller value of B will occupy lesser volume. Now that is directly you can understand, because B is directly related to the particle volume. So if this B value is less for this, obviously it will take lesser volume. Now lesser volume means what? It is more compressible. Compressible means what? Suppose from it is having a particular volume, you are compressing it. Now it will shrink. The volume will be shrink. When that is easier? When volume is already less, then the compressibility, or when you are trying to compress it, that process will be taking place very easily. So here you can say when B value order is like this, therefore compressibility order, that will also be smaller value of B will occupy lesser volume. So compressibility order is opposite. So B will be more compressible than D. So we have already cancelled 2 and 4 among 3 and 1. First part is common. Second part is saying B will be lesser compressible. Here it is saying B will be more compressible. So basically B is more compressible. So this is the order for small b value. This is the order for compressibility. This is very important information. So based on these, some different types of question may also be framed. So please give importance to this problem. It is really important. So option 1 is the correct option. That is, if we also consider the second part, this is the correct option. So now the next topic we are moving, which is liquefaction of gases. So we have, until now in this chapter, we have read all about gaseous state, different laws, then kinetic theory, and different laws are basically experimental observation, and kinetic theory, it is theoretical. And we have also seen in the last class how these two, that is whatever observations you have from different gaseous laws, how these observations can be explained on the basis of kinetic theory, that also we have seen. So the next thing, and then we have seen real gases, how they are deviating from ideal gases. Then the corresponding question, Van der Waals equation. And next is liquefaction of gases. That means how you can convert gas, which is a state of matter, to another matter form, which is liquid. Sometimes it is not possible to distinguish between these two states. It is true that there is some points that are common for both, and there are some points that are different for both. but in some cases they are really not distinguishable. Now, because of this that is fact that we are not able to distinguish, there are some situations. So you can say that liquids, as if you can consider them as if they are continuation of gas phase. Only difference is as if now they are present in small volume. Suppose you have any container where you have some gas particles, and now you have simply compressed the volume. So gas particles now they are close to each other. So as if when you have bringing them close in small region, small volume, then what will happen? The intermolecular interaction will increase because now the distance between particles are high, right? So as if gradually the liquid property will be arising there. So you can say liquids are as if continuation of gas phase when you are bringing them from large to small volume because of increase in intermolecular interaction. So what is the basic difference between liquid and gaseous? It is the distance between two particles. So in gaseous the distance is very high, there is almost negligible intermolecular interaction, but for liquids that is not the case. There is significant intermolecular interaction. So the process of liquefaction, it is basically a procedure by which substances in their gaseous state converted to liquid state. Now, how we can do so? What are the conditions that we have to maintain? That is, what temperature, pressure, volume, all these factors you have to take care. So these informations that is given by Andrews first by his well-known experiment, Andrews isotherm experiment, and there we have seen different isotherms for gases. Now isotherm, this term we know, it is the line in PV curve at different temperature, because isotherm means temperature fixed. So suppose you have 2 to 3 different temperature, T1, T2, T3, T4. So at each temperature, how the line, that is pressure volume line, is changing, from that plot we can get the conditions for liquefaction of gases. So Andrew is first who gave us the complete data on pressure, volume, temperature of a substance for both gaseous state as well as liquid state. Because if you know the information for both the state, then only you can will be able to understand the conditions where you can change the state of matter from gaseous to liquid, and that is liquefaction process. So what gas he has chosen? He has chosen carbon dioxide. He plotted isotherms for this gas at different temperature. Now remember, CO2 obviously it will not behave ideally. It is real gas. Okay. So the carb nature that you will see. Normally PV plot how it looks. Remember from Boyle's law we know temperature fixed. So P is inversely related to V. So when something, these two terms are inversely related and you have taken them in y-axis and x-axis, the nature of the curve, it is like this. Okay. So this is for ideal gas, but you may not get the same thing when you have taken real gas. So don't expect that the picture will be like this. Later he was found that real gases behave in a similar manner. So though he has started with carbon dioxide, but later it was also observed that other real gases, for suppose oxygen, nitrogen, ammonia, for other gases also, the more or less the basic nature of the curve is same. Obviously there will be a little bit difference, but other real gases, they are behaving in a similar way. Now when as it is isotherm curve, so different temperatures we will take, but at high temperature the isotherm look like that of ideal gas. So here that the plot that you are seeing that I have drawn, it is based on ideal gas, because Boyle's law is based on ideal gas, right? P is inversely related to V. So obviously the nature of the curve will be like this. But in Andrews experiment, the nature of the curve is not like this. Only when the temperature is high, then you can expect this type of nature, but only at high temperature. Fine. And we know this fact that I have told several times in previous classes, that real gases, they do not behave like ideal gases. There is so much deviation, but they can behave closely to ideal gases when the temperature is high and pressure is low. Okay, so here you can see one of these condition is met, which is high temperature. So obviously you can expect the isotherms line, they will appear just like ideal gases, close to ideal gases. Okay, so at high temperature, as now we look at of ideal gases. So this region of high temperature, if somehow we cross this temperature, what will happen? Liquefaction not possible. So there is a particular temperature below which you can do liquefaction, but above this temperature you cannot do liquefaction. And for different gases there is a particular value of temperature. So for CO2 there is a one value, for nitrogen there is another value. So different gases, different values of a particular temperature above which liquefaction process is not possible, even if the pressure is very high. Because when you are changing the state from gaseous to liquid, two things you have to keep in mind. So when it is gas, the particles are far from each other, but when they are liquid, they are close to each other. That means two things you have to take care. First of all, you have to increase pressure, then only they can come close to each other, the particles can come close to each other. So pressure should be increased and temperature should be decreased, because when temperature is very high, the molecules intermolecular interaction is not important. Now the particles can move from far from each other. So how, but your purpose is to bring them close so that the state of matter changed from gas to liquid, right? But if you are increasing temperature, how that is possible? So there must be increase in pressure and decrease in temperature. But there is a particular temperature above which this liquefaction is not possible, even if the pressure is very high. Okay, so we will see that in the next slide, where you will actually see the isotherms. As the temperature is lowered, the shape of the curve changes and there is considerable deviation from ideal behavior. So there is a particular temperature above which it will behave like ideal gases, but below that temperature, that is temperature when lower, the last line, now there is considerable deviation from ideal behavior. So this is the region where liquefaction is possible, but the particular temperature that I am saying several times, which is basically known as critical temperature, though we will gradually move to that point. But remember, this is a particular temperature for each gases above which liquefaction not possible, because above this point the gas will behave ideally, but below this temperature liquefaction possible, because now the gas is not behaving ideally. So this is the isotherms from this experiment done by Andrew. So as it is isotherm, obviously it is PV plot, and in this PV plot we have taken pressure y-axis, volume x-axis, and the lines that you are seeing, suppose see this line is at 50 degree, then the next line, which is gradually the temperature is lowered, 31, then the next line, this black one, this line I'm talking about, this is 30.98. So see 31, 30.98, very low difference, 31 and 30.98, it is almost same temperature, but still look at the difference. It is appearing like this, the black one, and the green one, which is at 31. There is obviously difference. So this much difference, there is a huge change you can observe in between these two lines. So this is the temperature, which is the critical temperature, which is denoted by T subscript C. So for CO2 gas, because this picture that you are seeing here, it is for carbon dioxide. So for CO2, this is the critical temperature above which you cannot do liquefaction. And look at the curve. The curve above this TC, I'm talking about this curve or this curve. Don't you think these are just like this that I have? You can expect from P inversely proportional to P. From that statement, this type of curve we expect. So these you can see only above temperature TC. The temperature when it is above TC, you can expect this type of nature. But just look below TC. Now the nature of the curve, it is like this. It is gradually moving down. Then there is a zone where pressure is fixed because this line is parallel to volume axis. That means pressure is fixed. Then once you reach the point B, it is again decreasing. Similarly, if you consider this line, so this is at 21.5, which is obviously lesser than critical temperature. Then we have another line 13, that is also lesser than TC. Here also this region where pressure is fixed. So similarly, you can also draw some other lines. But these 2 points for each isotherm, if you join, which 2 points? Those 2 points in between which pressure is fixed. So just if you choose those points, so here it is C and B, then these two, if you draw, that is join all these points, you will get this type of dome shape. So this is the shape. In this region, gas and liquid, these 2 states, they remain simultaneously. Now consider the second picture. Here you will be able to understand that in the dome shape region, gas plus liquid, they are existing together. So these 2 points, if you join like this, you will give this dome shape where gas liquid remain together. But this is critical temperature at point C, above which there is only gas in the right hand side zone. But if you consider this left hand side zone, there is liquid. Fine. But important point is here T4 greater than T3, that means T4 high, T3 less, TC less, then gradually it is decreasing and decreasing. So TC is that temperature, this black line, above which liquefaction not possible. See, if you are in this zone, whatever is the value of pressure, because we know when you increase pressure, the particles are coming close to each other and liquefaction possible. But once you cross this TC, even if the pressure is very high, then also it will not help. Only when you are in this region, this dome shape region, because here gas and liquid, they are coexisting, and you can say they are as if in equilibrium. That is a clear line. You cannot see, they are in equilibrium. Gas is converted to liquid, liquid is converted to gas simultaneously. So this is the region where liquefaction is possible. So in other region of this curve, liquefaction not possible. So from this type of curve, what important information we can get the value of TC, which is this temperature, and if you draw a corresponding line, just extrapolate it, it is cutting here. So this is the pressure which is at critical temperature, and that pressure is known as critical pressure. Similarly, from point C, if you extend this line, it will cut here. So this is the corresponding volume, I mean the volume at critical temperature. So that volume is known as critical volume. So 3 new terms we are seeing here: critical temperature, critical pressure, critical volume. Critical temperature is most, you have to give more importance. Once you know what is the value of critical temperature, now you can get that value of PC and BC. So suppose critical temperature, I am saying X degree centigrade. So now I will say for any gas where TC is X degree centigrade. Next, how you will know the value of PC and BC? So the definition will be the pressure at TC is PC. Volume at TC is VC. That means critical volume. Fine. So what explanation we can give here? Suppose you are in this region dash. So this is the high volume region. Now as you are moving towards this zone, one point will be reached when even if the volume is decreasing, but pressure is fixed. So this is the region where pressure is fixed. In this region only gas and liquid, they are existing together. Now see, look at this left hand side curve. So when you reach from V2 to V3, suppose you are moving from V2 to V3, so volume is decreasing, that is clear in the volume axis. Now the corresponding pressure is, just consider the corresponding, this is the point for V2, so the corresponding pressure is P2, and for V3 the corresponding pressure is somewhere here, because if you consider this line, it is cutting here. So just you have moved from V2 to V3. This is a small volume change. Look at the deviation from P2 to P3. Now the pressure is suddenly increased from P2 to P3 when you have moved from V2 to V3. So basically what is happening here? This zone where gas liquid both are present. Now when you are gradually decreasing the volume, that means you are compressing it. So when it is, you are compressing it, as now you have reached the zone of liquid, this zone is liquid. So when it is already in liquid zone, slight even if it is slight compression, then also there will be huge increase in pressure, because liquids are not compressible, gases are compressible. So when you are in liquid zone and still you are doing some compression, so a little compression will lead to very high increase in pressure, which is not in case of volume. We do not see that, right? So this is the explanation for this hand-loose isotherm. So important point is, from this you can, so this is for CO2. If we do the same thing for other real gases, you can get the value of TC, which is critical temperature. So the definition of critical temperature, it is defined as the temperature above which you cannot do liquefaction. Even if the pressure is very high, it will not help. And PC is minimum pressure required to liquefy 1 mole of gas at its critical temperature. VC is volume occupied by 1 mole of gas at its critical temperature and pressure. So first you have to give the definition of TC, because based on this you can get PC, and once you get PC, then you can understand what will be the VC. Because PC should be the minimum pressure at TC to liquefy not just any amount of gas, liquefy 1 mole of gas. Once you know PC and TC, now you can say the volume occupied by 1 mole of gas when it is present, already present in critical temperature and pressure, that volume is critical volume. So derivation of formula is not required, but you just have to remember these formulas. Critical temperature, it is 8A divided by 27 RB. R is universal gas constant, and these two are Van der Waals constant, right? And then we have critical pressure, which is A by 27 B square. Here again B term is present, and for VC it is simple, it is simply 3B. And remember, there is one more formula. What is Boyle temperature? That we have already seen in ideal gas equation. There we have seen that this is the temperature where deviation is not so high. That this is the temperature where you can expect a real gas to behave like an ideal gas. So that is the definition of Boyle temperature. Boyle temperature denoted by T subscript B, capital B, and that is also related to this A and V, which is A by RV. Fine. So these four formulas important to remember. So these three constant, these three means PC, VC, TC, together called critical constant. A gas below its critical temperature can be liquefied only. So remember the previous curve, the dome shape area, that is the area where liquefaction is possible by applying pressure. And A gas below its critical temperature, it is called vapor. So gas and vapor, obviously these two are not same. So gas is applicable, you can use it only for those substances who are under normal condition gas. For example, hydrogen, oxygen, carbon dioxide. Under normal condition, you know they are appearing as gaseous. They are not liquid. Only when you create some special condition, you are increasing pressure or bringing the temperature is in such a way, changing the temperature in such a way that they are converted to solid or liquid. But under normal condition, they are gaseous. So you can use the term gaseous for those substances which are under normal condition gas. But you will use the term vapor only in those cases for those substances who are under normal condition, not vapor. For example, water. Under normal condition, it is liquid. Only when you increase temperature, you are boiling it, you are getting some its gaseous form, and then you are calling it is vapor of water. But I mean, though sometimes by mistake we can say gas, but actually theoretically we call it vapor. Simply, if you consider bromine, which is under normal condition liquid, it appears as orangish yellow liquid. Iodine, under normal condition it is solid. But you will see that if you keep solid iodine in a container, there is some violet colored vapor. So that is not iodine gas, that is iodine vapor, because that is not the natural form of iodine. Similarly, from bromine liquid also, sometimes there is some gaseous appearance, but we should call it vapor. So that is the difference. So a gas, if we want to, if this type, that is another definition, the difference between gas and vapor. A gas below its critical temperature, it can be liquefied, and in that state you can call them vapor. So what is the importance of critical temperature? Because it is the temperature which is giving you the information, because you have to maintain this temperature, you have to keep it in mind if you are interested in doing some liquefaction of some gases, because you have to keep the gas below it, not above it, because otherwise it is not possible. So in the liquefaction of gases, this is crucial. Only when the gas below this TC, you can do liquefaction. So in this table, you can see TC value, PC value, and also VC value. Their units are also mentioned, Kelvin in atmosphere, and this is centimeter cube per mole. So if you see the gases which are under, that is very light gases, helium, then we have oxygen. Okay, so compared to this, if you consider carbon dioxide, or if you consider water, which is under normal condition, not gas, see, look at the value. Critical temperature is very, very high. Look at the value of ammonia, TC 405. So these two in this table, they are having the maximum value of TC, right? So what information we can draw? Gases where high TC is you are observing, such as ammonia, oxygen, sorry, not oxygen, water, then we have CO2, this one, we have, okay, CO2 is not present. So these are some of the gases. Ammonia, obviously, they can be easily liquefied by applying sufficient pressure, unlike the gases with low or very high TC. So for helium or oxygen or hydrogen, these are especially hydrogen and helium, their critical temperature is so low. So basically what is happening, when critical temperature is very high, you are getting a large area, because you have to be below TC. So if TC is already very low, so it is difficult for us to get towards more low value. But suppose if TC is already high, you are getting enough that is area where you can do the liquefaction. So that is why when TC is very high, accordingly the liquefaction process will also be easier. So you can easily liquefy ammonia, carbon dioxide, but liquefaction is not so easy for hydrogen or helium. And also remember, under normal condition, Though it is true that CO2 is also under normal condition gas, but helium and hydrogen, their behavior as if close towards ideal. So more close is the behavior towards ideal gas, liquefaction will be difficult. So the conclusion you can draw, higher is the critical temperature, higher will be its intermolecular force of attraction. So this is basically the actual reason. So when critical temperature is low means what? Just take hydrogen as example. Critical temperature low means what? That is the interaction between two hydrogen molecule, that is very, force of attraction is very weak. Okay, so that is the reason you cannot bring them close. But if critical temperature is very high, that means the interaction between two particles is already very high. So it will help us to bring them close together. That means liquefaction will be easier. So that is mentioned in the last slide. So see here the question is saying that Tc for water, ammonia, CO2 given. So this is for water, this is for ammonia, and this is for CO2, right? Here also it is given respectively when we start cooling from a temperature of 700. So suppose all these three gases are present at 700, same temperature, and gradually from 700 you have started the process of cooling. That means you are moving towards low temperature. Suppose from 700 you are decreasing it to 698, to 690, to 650, like this. So when you are cooling it, which will liquefy first, which will liquefy finally? So obviously, as you are bringing the temperature towards low value, suppose 680, then 640, so obviously first you are getting this value of water. So once the Tc is reached, suppose you have reached 647 and you are going below the value of 647. That means now suppose you are 640. So now you are below Tc. So liquefaction will start. So it will liquefy first, then ammonia, and finally CO2. So this is very easy to understand. Just from the value you can easily predict which will liquefy first, which will liquefy finally. Okay. Here we have a problem. The critical temperature and pressure of carbon dioxide gas given. So this is Tc value 304. This is Pc value 72.9. So Tc value, Pc value given for CO2. It is asking then what is the radius of CO2 molecule, assuming it to behave as van der Waals gas. So basically you have to use those formulas. Remember the formulas for Pc, Tc and Bc. Basically it is asking radius, but how you will get the radius? You need the value of small b. Okay. So from Tc and Bc, the formulas that we have already seen, we will use those formulas. So this is the value of Tc given. This is the value of Bc given. So this is the formula for Tc, 8a by 27 Rb. This is the formula for Pc. If we suppose this is equation 1, this is equation 2. If you take the ratio of these two equations, that is Tc by Pc in the left hand side, and in the right hand side, you will see here a term will be cancelled because here it is a by b, here it is a by b square. A will be cancelled, but b will remain. So from the ratio of Tc Pc, you are getting finally 8b by r. That means b is equal to RTC by 8Pc. Now put all the values. R value is 0.082. Then 304.2, which is temperature, already it is in Kelvin scale, so we don't have to change the unit. Then we have 8 and this is Pc. So as you have taken R value in liter atmosphere, so final value of B, obviously it should be like this. So in liter it is L per mole. Liter means it is dm cube. But if you change to cm cube, now it will be multiplied by 1000. Okay, so now it is 42.77. So from liter now we have changed it to centimeter cube, because see, final radius you have to finally reach in angstrom. So if you change it to centimeter, it will help you, because ultimately you have to reach to angstrom. Now this van der Waals B, this statement I have already mentioned. in when I have discussed A and B. So this B is basically 4 times the volume of a single molecule. So if the volume of a single molecule is Vm, then it should be 4 Vm equal to B. Fine. So from this information, next we can solve the problem. Because for a particular molecule volume, if we know, obviously you will be able to find the radius from the sphere volume formula, because you will now consider the gas molecule as if it is a sphere. So B is equal to 4 times to that of volume. But as there is mole, per mole, so you just cannot take a single molecule. You have to multiply it with Avogadro number, because there is per mole factor. So 4 into volume of a single sphere acid and also Avogadro number. So that is already equal to B, and B value we have just calculated 42.77 centimeter cube per mole. Okay, so both sides same unit. So from this you can find out the value of R3, which will be in centimeter. So R3 first, then root cube, it is 1.62 10 to the power minus 8 centimeter. Now 10 to the power minus 8 centimeter is equal to 1 angstrom. That means if you remove this term, ultimately you have to do the calculation in 1. Angstrom unit. So that is why 1.62, and it is matching with option A. See, there is another value also 16.2. If you do some slight mistake, there will be problem. So see, just 1 decimal, if you there is some error, it will be wrong option. Okay, so it will be 1.62, right? So correct option is option A. So we have already at the end of the session. Rest of the part we will do in the next class. Thank you for listening.